All right, congrats. This is the final districting video. We've made it. All right, so our last video was about this moment of inertia model. Sometimes I call it the Hess model because it was based on a paper written by Sid Hess. Okay, so we're going to take everything that we've done before, and now we'll just kind of add some constraints that will explicitly impose contiguity. Okay, so maybe to start, let's take that one that we just did. We'll save it, and let's duplicate it. And I'm going to rename it D7 moment of inertia starter. Let's see. Maybe I'll add contiguity here as part of the name. Okay. So this should all be the same as before. I should be able to just run all of this. So run all the steps except for the optimized part. I don't want to do that quite yet because I'm going to add a cell up here where I add these contiguity constraints. Okay, so maybe before I actually start adding these constraints, I should walk through what the constraints are. So let's go back to the PDF. So here's the Hess model that we just did. So let's scroll down. This is going to be the model that we ultimately code up. Okay, so this model is also based off of flow type ideas. So previously we had Fij was the flow across arc ij, but now we also have this V in the superscript, and that's representing the kind of the root of our district. So previously we had just one type of flow. Everything was the same type of flow. Now we're going to have different types of flow. We're going to have, you can think of it as like we have a green flow and a blue flow and a red flow and a purple flow. Each different node or county in our graph is going to have a different type of flow. Okay. So maybe what I can do first is just to define all of these variables in the model. So I'm going to have this flow variable for every edge ij, and this is actually a directed edge ij. So I'm going to have to work with a directed version of our graph. Maybe the first thing I should do is to get that directed version of our graph, which in a previous video we had done like this. So now let's add our flow variables. So I'll again call them F. Okay. So these flow variables we will have for every edge. So maybe I could do dg.edges, and for every vertex or root. So I could do dg.nodes or I could do g.nodes. They would end up being the same thing. Okay, so this is Fijv is the flow across arc ij that is sent from source or root node V. Okay. So what the constraints are going to say is as follows. Each one of these districts that I'm going to build is going to have a center node or a root node. And so that's going to be that node j for which xjj equals 1. So in this district, I don't know which one of these counties ends up being the center, but somewhere around here probably. And that county is going to be, you can think of it as like the yellow county. And so when it sends out flow, it only sends out yellow flow. And so we can send yellow flow across all of these edges in my yellow district. And that yellow flow has to reach all of these nodes in my district. So actually, each one of these nodes is assigned to the yellow root. And so each of them should consume 1 unit of yellow flow. And so that's what this constraint right here is saying, is that if you've got this node I different from j, and I is assigned to j, think of j as like the yellow node. If that's the case, we want that node I to consume a unit of yellow flow. So this right here says if xij is 1, if node I is assigned to the yellow node j, then it needs to consume a unit of flow. So you'll look here, this expression on the left-hand side is the net flow across node I. So we have some flow that's incoming, we have some flow that's outgoing, and whatever the difference is between those two is the amount that's being consumed. And so if we are assigned to the yellow root, then we should be consuming a unit of this yellow flow. Okay, so let's go ahead and code up this constraint, and it's going to be written for every j and for every I that's not equal to j. So add constraint or add constraints saying that, let's see, saying that if node I is assigned to node j, then node I must consume 1 unit of node j's flow. We're actually going to have a lot of constraints here, one for each I, and one for each j, so long as I different from j. Okay, so the constraint right-hand side is going to say xij, and then that left side is going to be the net flow across I. So let's see. This is going to be flow. How do we write it in the math model? Let's see. So we looked at flow across arc UI and IU. So here I'll say UI and IU. And this is all going to be of flow of type J, so that's this last part. And I want to sum over all neighbors. Okay, I think that's good. Okay, so we've done this constraint. Now let's do this constraint. So what is this constraint saying? This constraint says, let's say you're node I and you're assigned to the yellow node J. Then you should be able to accept flow of the yellow type. But if you try to send a green flow through a yellow node, then you're going to have problems. So we're only permitted to send yellow flow through the nodes that have been assigned to the yellow node. These yellow nodes cannot accept flow from the teal or blue nodes, whatever those are, It can't accept flow from the orange nodes, and so on. So what this is saying is, let's say if you have a node I that's not assigned to the yellow node, then this x would be 0, this right-hand side would be 0, and it would say, do not accept any incoming yellow flow. So if you've got a node over here, I don't know, let's say Payne County. Payne County in this map is teal colored, so it's not assigned to the yellow node, so that x Payne yellow variable is 0, and so it would not permit any of this yellow incoming flow. Okay, so add constraints saying that node I can receive flow of type J only if node I is assigned. So those are the quantifiers. We had a less than or equal to constraint. And let's see, what was on that right-hand side? It was xij times this n minus 1. So this n minus 1 is playing the role of a big M, like the previous model. Okay, so I could say M equals G dot number of nodes minus 1. So then this right-hand side would say M times xij. Okay, and then here I want all of the flow of type J that enters node I. So this is add up all flow going from U, sum U to node I of type J. And I want to sum over all U's in the of I. Okay, I think that's good. All right. So now I have these constraints and these constraints. So now all I need are these constraints. So what do these constraints say? This is for a particular J. So consider maybe one of the yellow nodes that's kind of the one that's selected as the root of this yellow district. And if you are the root of this district, then you shouldn't be accepting any flow into you. You should only be sending out flow to the rest of your district. And so that's essentially what this constraint is saying, is if you yourself are that root, then the flow of that yellow type that enters you, it shouldn't exist. That incoming flow of that yellow type should be 0. Okay. All right, so we're going to say that node J cannot receive flow of its own type. Okay, so something's going to equal 0, and this is going to be for every J and G dot nodes. So then we need to express what is that flow. So it's flow going from some node U to node J of type J, and we want to sum this over all U's. Okay, so I think that does it for our constraints. And so I want to make sure I do m.update here so that it doesn't print a whole bunch of things. Okay, it doesn't like that because I haven't imported network X. So let me do that right here. Okay, now it runs properly. Let's try to solve. Okay, and it solves again in a couple seconds. I think the rest of these should be the same. Let's give that a go. Okay, and I think this is the same districting plan as before. The district numbers might have changed a little bit. I'm not sure. The colors might have changed, but the true underlying districting plan I think is the same. Which no surprise there. When we didn't explicitly impose contiguity, we still got it for free. So in some sense, we didn't need the contiguity constraints for this particular instance, although generally speaking, we might have needed them. Okay, I think that does it for all of the districting examples. I hope this was helpful for you and for your project. If you have any troubles with any of these videos, please let me know or stop by office hours. All right.